Remember, we're setting up a perturbative calculation here. We take the inflaton field, phi of x and eta, and we decompose it into a part that is constant in space, only depends on time, and that is responsible for the bulk of the interaction with gravity. It's basically the zero mode of the inflaton field. And in addition, some extra field phi that is perturbing the inflaton field. It's the perturbation of the inflaton field that is space dependent. So the inflaton field in total is a zero mode plus something that can depend on space. And this part, the bulk part, we will treat classically so that we can explicitly work out its dynamics with gravity. And the space-dependent part, which is not that significantly interacting with gravity, it is interacting with gravity, but not to the extent that it would determine whether or not inflation takes place, for example. That part we will treat quantum field theoretically. Similarly, we treat the metric as partially classical, partially quantum. We will write the metric as the usual FRW metric in conformal time and co-moving space coordinates. Remember that the FRW metric can be written as a conformal prefactor, A naught squared of eta times the Minkowski metric. I'm writing here for the scale factor A naught because unlike previously where there was just one scale factor, now we have in effect that the universe is allowed to expand at different rates at different places, because we are now introducing a space dependence on the inflaton field and to the metric as well. So A naught is really, again, the zero mode of the metric. It is the part of the metric that does not depend on space, only depends on time. It's this thing that we will treat classically, and that will, through the Einstein equation, interact significantly with the classical part of the inflaton field, with the bulk of the inflaton field. Well, and then there's a perturbation of the metric. There is a space-dependent part of the metric. I'm calling it perturbation because we are assuming here that it is small. Our assumption in what we do next is always that the perturbation of the inflaton field, the space-dependent part, will be small, and also that the space-dependent part of the metric will be small. As we already discussed last time, the space-dependent part of the metric, this small perturbation, can be decomposed into three contributions. One contribution that can be expressed in terms of scalar fields, one contribution that can be expressed in terms of vector fields, and one contribution that is truly tensorial. So we introduced scalar fields E, B, psi, phi, and vector fields v and w, and a tensor field hij. Then the total metric, in the terminology where we use the metric to write the line element, decomposes into several parts. Namely, the total metric, the total line element is given by the FRW line element, plus a part that can be expressed in terms of scalar fields, vector fields, tensor fields. And concretely, just to remind you, this is how they look like. So the part of the metric perturbations that is expressible in terms of scalar fields looks like this. These are all possible combinations to put a scalar to work to write a spatial perturbation of the metric. And then we have perturbations to the metric that can be expressed in terms of vector fields. And then there is a perturbation to the metric that can be expressed in terms of a tensorial field only. And there will be conditions on these auxiliary functions h, w, v, psi, phi, b, and e. Our aim then will be to take those expressions for phi and g and plug them into the full action, and then consider perturbation, and then consider the expansion of the action that we obtain in this way. So we expand the field into something large plus a small perturbation. We expand the metric into the FRW part plus a small perturbation. And then we plug that into the total action, which is the gravity action plus the Klein-Gordon action plus other parts of the action for other fields that we are neglecting here. And then we expand the action to lowest order to take into account the lowest order contributions from those spatially dependent small inflaton field and metric contributions. The aim being that we then obtain an action for phi, an action for gamma, and therefore equations of motion for phi and equations of motion for gamma. Now clearly, when we do this, when we plug these two expansions into the action, we're going to get a whole number of terms. Because remember how complicated this thing was. Had a lot of arbitrary functions in there. So there are many terms when you write out the action in this way. However, it turns out that these terms can be simplified. And the reason is that we are free to choose our coordinate system. In FRW space-time, there is a preferred coordinate system, but really, fundamentally, there is no preferred coordinate system, and when space is curved, then this is quite obvious. And concretely, what we can choose is different notions of simultaneity. We can choose to slice space-time into space-like hypersurfaces one way or another way. There are infinitely many ways to define space-like hypersurfaces. And when we said that we are expressing metric perturbations in terms of scalar, vector, and tensorial functions, what we really meant was that these were spatially scalar, spatially vector, spatially tensorial functions. On each one of those space-like hypersurfaces. But in the full 3+1 dimensional picture, we are free to choose those space-like hypersurfaces, and that will therefore affect those spatially scalar, spatially vectorial, spatially tensorial functions. So what we can do is we can use this freedom to choose our slicing of space-time into space-like hypersurfaces in such a way that it will affect those functions in a way that we choose. We choose the space-like hypersurfaces one way, and those functions will behave accordingly, or we choose a different way, and those functions will be affected differently. So we'll have a lot of what is called gauge freedom in re-gauging what values these functions take by choosing our space-like hypersurfaces and the coordinate systems, the spatial coordinate systems on them. So by choosing the time variable and choosing the space variables accordingly. This is actually a very complicated business, and it has only been figured out, as far as I can tell, only been figured out perturbatively. Non-perturbatively, this is not yet fully understood. It took about 10 years to clarify this gauge question, and it would take too long and it would be rather tedious to go through the details. But here are the details. There's a paper by Brandenberger and others in which all the details are worked out. And then here is a paper that's much more recent, and it's relatively compact, where you can read on those details as well. The result of these studies is that as long as the inhomogeneities, as long as the space-dependent parts of the inflaton field in the metric are really small, as long as it's justified to think of the perturbations as being of first order, nearly all of those extra functions, the scalar, the vector, tensorial ones, nearly all of them can be eliminated by using a suitable choice of coordinate system. The only perturbations that really survive and that cannot be gotten rid of by choosing your coordinate system appropriately, that cannot be gotten rid of by choosing your slicing of space-time into space-like hypersurfaces cleverly, the only two that survive are these. First, the spatial tensor field, the part that is really tensorial, that cannot be expressed in terms of scalar and vector parts. This is the part that we called Hij. Now Hij, this truly tensorial part of the metric perturbations, is independent of T mu nu. Remember that when in the previous lecture we did the analog with electromagnetism, we discussed that a vector field, a three-dimensional vector field, as we always do in electromagnetism, can be decomposed into a gradient part and a curl part. And the curl part is divergence-free and the gradient part is curl-free. So the gradient part and the curl part obey certain conditions. And so similarly, here when we decompose the metric perturbations, then we also found a condition on the Hij. We'll later get back to them. For now, suffice it to say that these conditions mean that Hij is a part of the metric which is independent of the energy momentum tensor. In the same way that in electromagnetism, there are electromagnetic fields that do depend on charges and currents, and others that do not. Some electromagnetic fields are homogeneous solutions to the Maxwell equations. They are plane waves, they can just travel. And other electromagnetic fields only exist where there are charges or currents. And with gravity, it's the same thing. Those of you who took my course last term will remember the details of this. With gravity, it's the same thing. You can decompose the Riemann curvature tensor into a part that is so-called Weil curvature, independent of charges and currents, in this case masses and stresses, and a part which is the Ricci curvature, which is dependent on the energy momentum tensor. So it so happens that the metric perturbation that's truly tensorial in nature and that cannot be gauged away, that is part of the Weil curvature. It is not dependent on the energy momentum tensor. In other words, when the metric tensor fluctuates in this way, it's gravitational waves. These fluctuations can happen even in the vacuum. They don't depend on the existence of matter. And in particular, they don't care about whether or not the inflaton field does something, because the inflaton field would count as matter. It contributes to the energy momentum tensor. This part doesn't care about it. It's uncoupled from the inflaton field to first order in the perturbations. So there are perturbations to the metric that cannot be gauged away, that are truly tensorial in nature, and that are of the kind of curvature that is Weil curvature, independent of energy and stresses, or pressures, independent of the stress-energy tensor. This is the kind of curvature that LIGO is detecting. It's the kind of curvature that doesn't describe a local bloating or shrinking of space. It's the kind of curvature that would turn a ball into an ellipsoid but not change its volume. It would turn a circle into an ellipse without changing its area. That's the kind of curvature. You can roughly think of curvature as being of two kinds. There is the kind that is simply expansion and shrinkage, and then there's the kind that is deformation. It's a bit like take a rubber sheet and you can either, stretch it and shrink it, or you can distort it against itself. Except the analogy is not really that good because a rubber sheet really only has scalar curvature. In 2 dimensions, there is only scalar curvature. There is no, by scalar curvature, I mean expansion shrinkage. Only in higher dimensions do we really have this curvature that means that the space is distorted against itself. Oh. Okay, so I said that there are 2 perturbations that survive after we use our freedom to choose the space-like hypersurfaces in space-time and the coordinate system on each one of those space-like hypersurfaces. One of them is this tensorial curvature, and the second is a spatially scalar field, let's call it R, which is made out of the inflaton field and some components of the metric. Now, so what I'm saying here is that there is a degree of freedom that is made out of both the inflaton field and the metric, and this combined degree of freedom is gauge independent. Now, how come that there could be a combined degree of freedom? Well, it's because curvature has a degree of freedom that means bloating and shrinking, and it is coupled to matter. This is what matter does. And the inflaton field provides an example of matter. It contributes to the energy momentum tensor. Depending on what the inflaton field does, gravity will, the scalar part of gravity will react to that, and vice versa. They're coupled degrees of freedom. So the Einstein equation that couples the two, couples the spatial perturbations of the inflaton field to, as it happens, one of the scalar components of the perturbations of the metric. If you look at the psi, where is it? Here it is. You see this component of the perturbation of the metric, that's the one that survives after using the freedom to choose our coordinate system. And here is this magical thing, and we will discuss in all detail why it takes this wild form. So here we have a certain scalar part of the metric perturbations, of this small space-dependent perturbations to the metric of scalar nature. That's contributing to our variable r. R being that gauge invariant quantity that's made out of a part of the metric and a part of the inflaton field. But look how the inflaton field goes into this. Phi of x and eta is the perturbation of the inflaton field, which is space-dependent, and it comes with this prefactor. A naught prime, which is the derivative of the scale factor with respect to the conformal time, divided by the scale factor, and you remember A naught is the FRW scale factor. And here we have the bulk inflaton field, phi naught, the zero mode of the inflaton field, differentiated with respect to the conformal time, and then we take 1 over that. So we have this complicated expression here, time-dependent complicated expression in front of the inflaton field, and here we have this scalar contribution from the metric. The claim is that this entire expression here is gauge invariant. In particular, what this means also is that just the inflaton field's perturbation is not gauge invariant. Just the scalar part of the metric itself is also not gauge invariant. In other words, they don't have physical meaning on their own. what values they take depends on what coordinate system we choose. Whereas this whole combination is gauge invariant. So physically, what is this? Okay, so this is from the metric, that's from the inflaton field. Or let me put the question differently. If this is the physical variable, then what is really fluctuating? Are we dealing with quantum fluctuations of the inflaton field? Or are we dealing with quantum fluctuations of the metric? Is it the amplitude of the inflaton field that is varying in a quantum way, fluctuating? Or is space-time bloating and shrinking locally in a quantum way? Which is it? This seems to be a linear combination of both of them. Now it turns out that both points of views are correct. You can say that what's going on is really that the inflaton field is fluctuating. And never mind the metric, the curvature. It's not happening. There is no bloating or shrinking of space-time curvature. No, no, no. The only thing that happens is that the inflaton field is fluctuating. But you can also say, no, 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 the inflaton field is not fluctuating at all. The amplitude is fine. It's just, it's not space-dependent. It's the metric that's fluctuating. There's a local bloating and shrinking going on. And the 2 points of view differ only by choices of coordinates. You can choose your coordinates one way or the other such that this term goes away and all you're dealing with is this. In which case you would say, oh, I see, it's just fluctuations of the inflaton field. But you can also choose your coordinate system in such a way that this goes away, the fluctuations in phi, the space dependence of phi goes away, and you're only left with that. And then you would say, oh no, it's only gravity that's fluctuating here. Let's do those 2 choices of coordinates. So here's the first choice. Let us foliate space-time into space-like hypersurfaces such that the inflaton field does not vary. So the fluctuations, the space dependence of the inflaton field goes away. In other words, we look at the space-time and we check what are the values of phi, and then we slice space-time in such a way that we go along the surface of equal phi, and the surface of equal phi will for us a surface of equal time. We just choose equal phi to be equal time. Now, can you imagine that it may not always be possible? But it will always be possible if the value of phi is changing overall, has a tendency to overall change. And remember, we have that assumption. We have slow roll inflation. We say that the bulk of the inflaton field, the zero mode of it, the part that's constant in time, takes a certain value at the beginning of inflation, and then it slowly rolls, it slowly diminishes that value until eventually inflation ends. So if the bulk of the inflaton field overall is slowly diminishing, then it means that we will always be successful in slicing space-time into space-like hypersurfaces, where each space-like hypersurface is equal phi. Because think about it this way. Imagine you do this slicing and you find, oh, there's a bump, there's extra phi, I have to go around it. You can always go around it because overall there's this tendency of phi to diminish. We will later see that we run into a problem if phi is not having a tendency to overall vanish, if it's not slow roll inflation. For example, if we look at the theta inflation, where phi would be constant. In this case, we couldn't do this, and we will see later in more detail why that is going on. Okay, so one choice of foliating space-time into space-like hypersurfaces, one choice of coordinate system is to choose time to be using phi, and I don't mean the little phi, I mean the capital phi, the bulk of it, as a kind of clock. And equal phi is equal time. And so as you go along one of those space-like hypersurfaces, you have absolutely no space dependence of phi. The little phi is 0. In this case, our variable r doesn't have any of this. It's always 0, and we only have curvature, a scalar kind of curvature. So in this case, if we choose our coordinate system in this way, then the variable r, the gauge invariant variable r, expresses purely metric fluctuations of a scalar kind. And it turns out that technically these fluctuations are fluctuations in the intrinsic curvature, which is like local bloating or shrinkage within the space-like hypersurface. So not relative to the 3 plus 1 dimensional spacetime, but just local to the 3-dimensional spacetime. You can think of it as a gravitational potential that's either a little lower or a little higher, which means that if you had photons emitted from there, then they would either roll down a potential hill, a gravitational potential hill, or climb out of a potential hole. We will later come back to this because it will be the origin of the temperature fluctuations in the CMB. Basically, as we will see, it's not that the CMB originally had, because of quantum fluctuations, different temperatures that we see now. No, it was all the temperature, the temperature was really the same everywhere. But because of gravity fluctuations, the light had to climb out of some potential wells or was rolling down potential hills to us. And so what we now see as temperature fluctuations in the CMB really has its origin in gravitational redshift, gravitational blue shift, rather than different temperatures. But we will have to see why. I mean, what I just said is that basically this is a preferred way of looking at it. It doesn't look like that at the moment. It's just one choice of coordinate system. Okay, it's just one choice of coordinate system, one choice of slicing spacetime into space-like hypersurfaces. Why this particular point of view will be preferred later on, I will explain a little later. So this is one way of foliating spacetime. Here's another way of foliating spacetime, namely, you can foliate spacetime in such a way into space-like hypersurfaces that we choose equal time to be where psi, this particular scalar variable, is a constant and not phi. So in this case, we look at the space-time, a 3 plus 1 dimensional space-time, and now we slice and we define a hypersurface of equal time in such a way that we go around any curvature bumps. And in this way, we again arrive at space-like hypersurfaces, but now the psi is vanishing. Along any one of those space-like hypersurfaces, there is no intrinsic curvature. We cut around that. We cut along, we cut a surface such that there is no curvature on it. But instead, now in this gauge-independent variable, this is vanishing, and all of the degrees of freedom are now seen as sitting in the spatial perturbations of the inflaton field. Now, this might be the right time to wonder why this stuff here? Where does that come from? Doesn't look very plausible. I mean, it's perhaps, I hope, became plausible why, you can shift the degree of freedom R, which is really the physical degree of freedom, by choice of coordinate system, either into the metric or the inflaton field, but why these prefactors? So let's try to get some intuition for that. So the question is, why is that prefactor here of that particular form, A prime over A, phi over capital Phi prime, where capital Phi is the zero mode of the inflaton field. Okay, so here's the answer. The inflaton's inhomogeneities, think about it physically, the inflaton's inhomogeneities imply locally varying expansion rates. Because when the inflaton field's amplitude is varying in space, it means that the inflaton field's potential is varying in space. But the potential of the inflaton field is what drives the expansion. So some regions will be ahead, some regions will lag behind, depend in the expansion, the overall expansion, because the field at some places will have a larger potential, some places a smaller potential. So changing the space-time slicing from scenario A or from gauge A to gauge B has to turn pure intrinsic curvature, which is local bloating, which is delta A over A, this is the expansion, that's the variation of the expansion, into pure inflaton fluctuations. Right? So what this gauge-independent variable is expressing is an equivalence of metric perturbations, which is a change in local bloating or shrinkage to a change in the inflaton field. And naturally, they wouldn't be of the same kind. And what this prefactor is doing is it's making them of the same kind so that you can add them. But how? Okay, so here's a sketch of that. Let us look at fluctuations in the local bloating or shrinkage. A fluctuation in the scale factor divided by the scale factor, I'm considering that quantity because it comes up. So what is the fluctuation of the local fluctuation of the scale factor divided by the scale factor? I'm just dividing it by the scale factor because it turns out that this is the expression that that comes up in this gauge invariant quantity R. So the local variation of the scale factor divided by the scale factor can be written as 1 over the scale factor. I'm just carrying forward 1 over A. And then it's the variation of A with respect to the bulk inflaton field, so the zero mode of the inflaton field. This is just the chain rule. And then carrying again forward the 1 over A, we can write it as dA by d eta by d phi. Again, just the chain rule. And here we have the time dependence of the scale factor. Here we have the time dependence of the inflaton field. It's 1 over it, right? It's d phi by d eta. And we can write this as A prime over A, 1 over phi prime delta phi, which is exactly the expression that we had up here. It's exactly this expression. So we recognize now this expression as being essentially delta A over A, which is the perturbations of it's the local bloating or shrinkage. And that is, of course, of the same kind of what the metric perturbation does. So then, what are the consequences of that?
Can I ask a question?
Yep.
This R guy that we've been considering, or V, is it R? V?
It's an R.
R, great. Is your statement that it's like the only gauge invariant function of the two perturbation quantities?
It is.
That's the statement?
Yeah,
okay.
it is.
Great.
Yeah. Can't prove that here. It's lengthy, but that's the claim. That is the claim. Yes, there are only 2 gauge invariant degrees of freedom. This one and the H field, the tensorial part of the metric, which is fluctuating on its own as it's the gravitational wave part. Now the H field actually has 2 degrees of freedom. So overall, it's like 3 of them.
We'll talk about those guys.
Yeah, we will, of course. Okay, so now that we're a little bit familiar with this quantity R, let's see how it behaves. See, there's something critical about it that will invalidate part of what we did earlier. Let me show you. Okay, so let us look at the this variable r. It is this expression. Everything depends here on eta, on time and space. And remember that we can choose this to look like, by choosing our coordinate system, we can choose it to look like being only fluctuations in the intrinsic curvature or being only fluctuations in the inflaton field. Often people will just speak of it as fluctuations in the intrinsic curvature, but never mind, it's both. Now from this expression, we can read off that it seems that this thing can explode. It can grow very, very large for no good reason. Namely, it can grow large when the inflation is close to being de Sitter inflation. And this is not really a physical phenomenon, but it's a phenomenon that has to do with not being able to control fully the perturbation theory. So let us look at this gauge invariant quantity. What happens when our inflation is close to being de Sitter inflation, when the expansion is close to being exponential? Remember that de Sitter inflation has this peculiar property that the expansion is exponential with a Hubble constant, which means the horizon is of a constant size. Which means that the field that causes the de Sitter inflation has a constant value, because its potential has a constant value, right? Remember that the square root of the potential is the coefficient in the exponential. So de Sitter inflation means constant horizon size, means constant value for the potential. Constant value for the temporary cosmological constant means constant value for phi, for the zero mode of the phi. We can't have that here because it's in the denominator. You see, phi naught, the zero mode's evolution, its derivative is in the denominator here. If we had strict de Sitter inflation, that would be infinite. Very bad. But we do know that this is not because the fluctuations themselves really grow infinite in size. No, it has to do with the difficulty of controlling the perturbation theory. Remember, this is a gauge invariant quantity, and how is it a gauge invariant quantity? Remember, we can choose our slicing of spacetime into space-like hypersurfaces in two extreme ways. We can go around the fluctuations of phi or go around the fluctuations of the curvature, and then we have either constant curvature equal time surfaces or constant phi equal time surfaces. But as we discussed earlier, it only works if there's an overall trend of phi diminishing, so that we are sure that we can always go sufficiently far around, like phi is, let's say, too large. Well, we just go a little later in time, and then phi will have diminished, right? So we can always go around and slice things appropriately if there's an overall trend of decay. It's exactly the reason why it blows up if there is no overall trend, if phi prime is equal to 0. So it doesn't mean that the fluctuations grow totally out of hand. It means primarily that our perturbation theory goes wrong. That's what it means. Remember that in all of this, we are assuming that our perturbations are small. So as soon as this thing goes large, we should not think, oh, it's really large. We should think, damn it, our calculations are no longer working. Okay? So we will have to verify that we are in the right regime where this is actually making sense. We shouldn't be too close to de Sitter inflation, otherwise we have to go back and rethink our calculations. And here's how it comes about. So if we have de Sitter inflation exactly, then h is a constant up there, and therefore a dot over a, which is h, and remember the dot stands for differentiation with respect to proper type. whereas the prime stands for differentiation with respect to conformal time. So our h is a dot over a, which is a constant. Therefore, the phi is a constant. Therefore, phi prime is 0, and therefore this thing blows up. And remember that the Hubble constant at the zeta phase is square root of the potential, up to a factor of square root of 3. This is just a discussion that we already had, saying that d phi by d eta occurs in here, in the calculation of this prefactor here, and the phi prime is the change of phi with respect to eta, and if that is very small, then this thing becomes very large, and our r variable blows up. So it would mean that another way of looking at it is this. We had two preferred coordinate systems. One where there was only intrinsic curvature, and one coordinate system where there was only fluctuations in the inflaton field. And you can think of this intuitively as having one way of slicing space-time into space-like hypersurfaces, and another way to do it. And the two definitions of equal time would differ. So you have that the two space-like hypersurfaces of equal time would actually be nowhere near the same. They would, in general, they will be sort of parallel and so on, right? So you have, if you start out at equal time at some event, and then you complete the space-like hypersurface either by method A or by method B, one way or the other, then you get two different space-like hypersurfaces, and they can be quite a distance apart from another. And when this happens, when we are close to the zeta inflation, then they can be very large away from each other, and in fact, arbitrarily large away from each other if it's the zeta inflation. So that invalidates the idea that we can still do it perturbatively. Because when we say that R is a gauge invariant quantity, what we really claim is that it's gauge invariant under small diffeomorphisms, small changes of coordinate system. It's not really gauge invariant, not fully. Okay, so could this be a problem that invalidates our whole calculations here? Well, let's see. The observations are, we can basically observe the size of R. We can basically observe the size of those fluctuations, as we will discuss later on. We can make predictions for the temperature fluctuations, and the size of the temperature fluctuations in the CMB has to do with how much the photons emitted when the CMB was formed had to climb out of a gravitational well or coming down from a gravitational hill. And from that, we can infer that the fluctuations in R ought to have been of order about 10 to the minus 5. So the delta A over A would be about 10 to the minus 5. That's one indication that we are in the right regime. R is small enough. 10 to the minus 5 is pretty small. But in addition, there's also evidence that the Hubble radius during inflation actually increased, which is to say that the Hubble constant decreased, which is to say that the amount of fluctuation amplification decreased, which is to say that inflation really took place in a decelerated manner. It was, of course, very much accelerating the universe, but the coefficient was not a constant in the exponential. It was sub-exponential. Right? So at the beginning of the inflation, the horizon size was a certain size, and at the end of the inflation, the horizon size was larger. The expansion was less dramatic. The amplification of the fluctuations was less dramatic. The later amplified fluctuations are smaller in size than the earlier amplified fluctuations. So there's experimental evidence for that, which tells us that this phi prime was actually small, was finite enough. It was not too close to 0. It's a firm prediction of inflation that should have happened, that the amount of amplification decreased over time during inflation. Now, let's see. We were talking about gauge invariance. You can choose your space-like hypersurfaces one way or another. You can view those fluctuations as either being fluctuations of the inflaton field or as being fluctuations of the scalar part of the metric. Is there no preferred way? Or is there a preferred way? Is the gauge invariance broken or not? Is there a preferred gauge? Does nature single out a gauge? The answer is twofold. During inflation, no. It was gauge invariant. During inflation, you could equally say that all the fluctuations were curvature fluctuations, or I'm talking about the scalar fluctuations. The Hij is a different story. So during inflation, you could say that, well, the fluctuations were just curvature fluctuations, scalar curvature, intrinsic curvature fluctuations. Or you could say it's all inflaton field fluctuations, depending on your choice of coordinate system. But at the end of inflation, one coordinate system was preferred. Can you guess which one? Yes?
Metric fluctuations. But the reason is because your perturbation theory that disappears because your inflaton field becomes constant, right?
Yes, exactly. The reason is that the end of inflation is defined by the inflaton field going downhill, right? Inflation ends exactly when the inflaton field says it ends, when it goes down, right? And then all its energy goes into the production of the hot Big Bang soup and so on. So in other words, the end of inflation is defined by what the inflaton field does, not by what the scalar part of the metric does. And therefore, the end of inflation is a snapshot in time, which is a space-like hypersurface of equal phi. And therefore, it's the fluctuations in the metric that are then the real ones. That's why it is fair to say that when at the end of inflation, the universe was filled with hot gas, it was at the same temperature everywhere. But the photons that, we had this huge, this plasma, it took another 100,000 years to cool down so that eventually, after the end of inflation, it took another 100,000 years for the plasma to cool down to the extent that it became transparent. Namely, when it reached about on the order of 1,000 Kelvin, when charges could combine to form neutral atoms, hydrogen. And then the universe became transparent, and all the photons that were racing around at the time could then travel freely, and these are the CMB photons that we see now. The point is that at the end of inflation, what was imprinted on space-time was a pattern of gravitational wells and hills, and 100,000 years later, when the photons were freed to travel through the universe, then they had to either climb out of such a potential well or came down from a potential hill, and so we now see this as temperature fluctuations because of the corresponding. Yep.
One question. In principle, it's not a choice of coordinates which is preferred. It's just that this term, this first term, although the phi prime becomes zero there, and you have infinity, also your fluctuations become zero, right? The delta phi. So in principle, that term can be zero. In your decomposition of R,
right?
At the end of inflation, not only is phi prime equal to zero, phi zero prime equal to zero, but your variation of phi also is zero, right?
Why do you say that?
Because you have reached the bottom of the potential.
Yes, but why do you say that the variations would vanish?
Variations don't vanish.
Yeah.
No, that's not true. Yeah,
right. Okay. All right. So, but the point is, during inflation, you have a choice of coordinate system, but at the end, the physics of it is determined by what phi does, and so phi singles out a particular slicing, and that's where we go from there. Where are we?
So you say that this has nothing to do with the fact that you have done perturbation theory?
No, I don't think so. No, it's the physics that determines when inflation ends. So when inflation ends is when the inflaton field says it ends. And that is what singles out.
Right, but that there are no two descriptions for that end is a bit strange. I mean, that there is no coordinate thing there.
Okay, no, that's good point, good point. The thing is that this is also the moment when these fluctuations went from being virtual fluctuations to becoming real fluctuations. That's a whole different story that one can give several lectures about, right? So, how is it that at the end of inflation, and it happens when the phi field drops down, and when all the energy in the inflaton potential goes into the production of all this hot plasma, the so-called reheating process, how is it that suddenly we have real fluctuations? Now, there has been some controversy about this, but it seems that the consensus is that all those other particles are essentially acting as observers of what went on. Before that, it was all just virtual, but once you had all those other particles involved, they were basically observers that decohered the fluctuations that were going on. And at that point, you have produced facts, so to speak. You have that, you have this plasma there, it has certain fluctuations, and there's no going back. You can no longer say that this is another kind of fluctuations, and so on. An alternative view was that, one moment, Guillaume. An alternative view was this, that when you, remember decoherence comes about when you couple a system to degrees of freedom that you then trace over. A pure state goes into a mixed state in this way. Now, what we saw here is that when a mode crosses the horizon, then its 2 degrees of freedom, the sine and the cosine part of a wave, the real part, the imaginary part, they go different ways after horizon crossing. You have that one of those 2 degrees of freedom goes to 0, the other one goes to a constant. In fact, in the frictionless variables, you have that it goes to infinity. And some have argued that the part that goes to 0 is in essence no longer observable, or to be sort of traced over, and that would decohere it. Well, there is some work on that by Starobinsky and others. I don't find it very convincing. I think it's much more convincing to think of all the matter as being the observers of the fluctuations. Oops. Okay, so we wanted to expand the action. Remember, all of this was really going off on a tangent in a way, because what we really want to do is, of course, calculate those fluctuations. And what we had done is we had expanded the inflaton field and the metric, and then we wanted to plug that into the action and find out what the equations of motion therefore are for our variable r and for the hij. For the 2 gauge-independent quantities. What are the equations of motion? What happens when we quantize them? What kind of fluctuations do they have? It's just that we spent quite a bit of time understanding the r variable a little better. But now we are back to the main trajectory, which is to find out how the equations of motion look like for the degrees of freedom that are left after we make use of our choice of coordinate system and space-like hypersurfaces slicing. So we take the total action here, the Einstein action and the Klein-Gordon action, and we plug in the expansion of the inflaton field into a 0 mode plus spatial components, and we plug in the expansion of the metric in terms of the FRW metric plus those scalar vector tensor perturbations. And we make use of the fact that we can eliminate almost all of the degrees of freedom in the metric. We can identify them as being diffeomorphism variant quantities, and we are left with just the degrees of freedom hij and the r. And then we can express to lowest order what the action is. And what we find is that the action is this expression for the bulk, for the 0 mode variables, plus a part for the scalar degrees of freedom, the r, and a part for the tensorial degrees of freedom, the hij. And for the scalar degrees of freedom, for our R variable, the action comes out to be this. It's a little tedious to put it in there, but just about homework size, I suppose. You could do this. So the action for the R variable, after everything is said and done, is this. Now let's look at this thing. How does that look like? Well, we have here the Minkowski metric, and then we have just the derivatives, d mu, d nu of the R field, as if it was a regular Klein-Gordon field. And we have here this factor z squared of eta in front of it. This actually looks very much like the action of the Klein-Gordon field that we had earlier. If you remember how that looked like, the action of the Klein-Gordon field in conformal time and co-moving space coordinates, it looked just like this, except that we had the Klein-Gordon field here, and that we didn't have a z here, whatever that z might be. We had a squared here, the scale factor squared. So if we had the scale factor squared here, and this was the inflaton field, then we would say, oh, we know that one. Just the Klein-Gordon action in conformal time and co-moving space coordinates. But here we have this action with R being our gauge invariant scalar quantity made out of intrinsic curvature and the inflaton perturbations. And then this Z variable is this expression here. It's A naught squared over A naught prime times phi naught prime. Again, one of those weird quantities here. But actually, even though it looks complicated, in practice, it's pretty close to being A itself, pretty close to being A of eta. And the reason is that since we are not working with the zeta inflation, but also not all too far away from it, we have that A prime over A is almost a constant. Okay, it's slowly varying, it's slow roll. So A prime over A is almost a constant. And that's something we have here. We have A prime over A. It's almost a constant. But we are left with one factor of A, right? So A, and then we have also an A prime over A. But the A prime over A is basically a constant. So the time dependence in this thing is basically A. And what is that? Well, that's a phi prime. But phi prime is, again, because it's slow roll, pretty much a constant. So overall, the time dependence of this is basically the time dependence of A. A little bit modified because it's slow roll. But the slower the slow roll, the closer this is to being A. So essentially, this is just like one of those actions that we considered before, the action that we considered before. Klein-Gordon action, except that instead of having an A of eta, we have a Z of eta. But that doesn't make our calculations any harder. Because whether it's called A or Z, it's just some scalar time-dependent function in front of it. So in order to quantize this, we can use all the tools that we used before, except that we have to keep in mind, cannot do it for the zeta. Perturbation theory would not be right. So that's the scalar part of the perturbative action. And then there is also a tensorial part. Oh, I already mentioned that. This is the Klein-Gordon action as we had it in previous lectures. Inflaton field here, and here was the A squared term. So it's very much similar to what we have now for the R field, except that A squared is Z squared up there. Okay, and then when we do the perturbation theory of the action, we find that the tensor part has this action. The action for the Hij field, for the tensorial perturbation of the metric, is given by this. Minkowski metric, and then scale factor in front, and in this case, it's really just the A squared. And then here we have d mu of the field, d nu of the field. So that is actually exactly the action that we had before. We can exactly reuse what we had before, except that can't do it for the zeta. It has to be a little bit slower than de Sitter. But it's basically the same thing. The only difference is that we have indices here, hij, and we will have to study exactly what to do with them. But it's clear that it's really just the Klein-Gordon action for H. Yep.
So there's no coupling between distinct ij and I prime j prime. Is this whole action free in all of the perturbations?
You're like tracing, right? There's a sum there.
Yeah, you're summing over the I and j. But later we will see. Remember that the hij are not completely free, because just like in electromagnetism, when you decompose a field into curl and gradient, then, for example, the curl part doesn't have a divergence, and so similarly here, the H field obeys certain conditions, and this will allow us to reduce the number of independent degrees to identify that H really doesn't have 3 by 3 degrees of freedom. It has way fewer. It has actually only 2, just to say 2 polarizations.
Is it free then in R?
In R?
Like not this action, the one that you said showed previously.
Well, yes, the R is not interacting with the H. That's right.
But does it have any interaction term?
Oh yeah, in higher order, since gravity is nonlinear, everything is going to interact with everything. This is just the lowest order.
Oh, okay.
Yeah. Ultimately, we do expect nonlinearities, that's right. And that boils down eventually to non-Gaussianities in the prediction. Okay, I'm anticipating things a little bit. But remember that when you have a free quantum field theory, no interaction vertices, then your 2-point functions are what is called Gaussian. The statistics is Gaussian, which means that you can predict what the 4-point functions, 6-point functions, 8-point functions are doing from just the 2-point functions. That is Gaussianity, right? And what you're saying here is that, okay, so we predict right away Gaussianity, right? Whatever they actually are, they have to be Gaussian because of this. That's true. That is a firm prediction of inflation to lowest order. But because ultimately gravity will make everything interact with everything. Oh my God. Forgot. Ultimately, we do expect non-Gaussianity. And of course, this is a huge experimental effort. There's very high interest in detecting firm evidence for non-Gaussianity because it tells us where the nonlinearities kick in, or if it happens too early, it's an indication against inflation. So people are definitely looking for that, for signs of interactions on non-Gaussianity.
For our purposes here, though, like when we quantize these perturbations, are the quantum field theories going to be free? Are they going to?
Yes.
Okay.
Yes. For our purposes, lowest order. It's a free quantum field theory, and we do it independently for H and independently for R. Yeah, they're not going to be interacting. That's right. They will have correlated predictions, but that's only because they are working on the same A of eta, the same basic scale factor, right? So if whatever scale factor you use, it will make predictions for R, it will lead to predictions for H. And since they both come from the same A, there's always going to be correlations between them. But they're not dynamical, they're just causally because we use the same underlying background space-time. Okay, so the quantization then of those 2 degrees of freedom, R and hij. The equations of motion, because of we've just identified what the action is, so we can identify what the equations of motion are. The equation of motion for the R field has to be this, because it would be this if instead of Z we had an A. We did the calculation already, right? When you have an action of that form with this scalar prefactor there, then you get this equation of motion. For example, for the tensor field, this must be the equation of motion because it's the equation of motion for the Klein-Gordon field. You have in the action the conformal prefactor A squared, that translates into this term for the equation of motion. And similarly, if you have the conformal prefactor z squared, then this must lead to it. This must lead to this factor in the equation of motion. So the gauge invariant variable r has the dynamics described by this equation of motion here, and the tensor perturbations, the h has this equation of motion. Both of them are Klein-Gordon equations. The only slight difference is really in what the z is as compared to the a. But as we already discussed, when we have slow roll, the slower the roll, the more is the z like the a.
Excuse me, what is tau
Where's tau?
in A depends?
R.
That's a mistake. It's eta, of course. Yeah, it ought to be eta. Thanks. Yeah. And sometimes the conformal time is called tau. So, I don't know. Yeah, I think in my papers I always call it tau, and so somehow that just slipped in. Freudian thing. Okay. So now how do we deal with these two equations of motion? Well, the same way we dealt with the Klein-Gordon equation previously. We choose a new variable, new field variable, such that we get rid of the friction term here and there. And we can do that in complete analogy to what we did before. Previously, we had the Klein-Gordon field phi, and we defined a rescaled field chi by putting in the scale factor, and then that led us to a new Klein-Gordon equation for the field chi, which had the advantage that it didn't have any friction term, and instead we just had a time-dependent harmonic oscillator, and we discussed in great detail how to do its quantization. We can do the same thing now. We take the scalar component first. Here's the R field again. It evolves as if Z were the scale factor. So the trick is going to be to multiply it with Z. Actually, the literature has a minus sign in here. It doesn't really matter. It's just a convention. And then we define a new field U. And that field U is a rescaled version of the R. And its equation of motion is again a Klein-Gordon equation without a friction, but with a time-dependent frequency. This variable will be called the Mukhanov variable, the U. Now, the tensor components, the gravitational wave part, we proceed the same way. We take the original degree of freedom, h, and we multiply with the scale factor to obtain a new set of variables, whose equation of motion is then, again, without the friction term, only has a time-dependent harmonic oscillator part. The literature has it that we are not only multiplying with A, but also with this factor. It's just a matter of convenience. So to stick with the literature, we put this factor in here. It completely drops out of the equation of motion, of course, because it's a linear equation of motion. But of course, not to get things wrong, you have to keep in mind that this is how it's done in the literature. Now, as we discussed earlier, it's not the case that all the Hij are independent degrees of freedom. Let's see what degrees of freedom we really have. I remember that just like a curl field in electromagnetism doesn't have a divergence, and a gradient field doesn't have a curl. Here we have, in the decomposition of the metric, that the Hij field has the property that it is trace-free, and that indicates that it is, for those of you who've taken my course last term, let me remind you, and for the others, let me tell you that the tracelessness here means that it's the kind of curvature that is not changing the volume of a ball or the area of a circle, it's only deforming them. As opposed to what the R does, which is to locally bloat and shrink space-time. It can actually make a ball larger or shrink it, whereas this curvature is wild curvature. It can only deform without growing or shrinking things. So that's a key condition here. Of course, it has to be symmetric too, because the metric is. And in particular, we also have, as it turns out, would be too lengthy to prove, that d by dxi of hi is vanishing. Or if you write it in momentum space, then it's ki hij equal to 0. This is similar to what we have in electromagnetism as well. Gravitational waves are propagating at the speed of light, which means that they do not have a longitudinal degree of freedom. And this is saying that the hij doesn't have a longitudinal degree of freedom. If you project onto the longitudinal, onto the direction of travel, then you get 0. It's just a transversal wave. So this means that this equation here has no solutions that would be propagating in that point in the direction of propagation. So the hij describes transversal waves, like, for example, electromagnetic waves, but also, for example, just like tectonic shear waves, if you want to some intuition. Tectonic shear waves are, when rock is, when an earthquake happens, then two kinds of waves will be produced. One is where rock presses on rock, and that is a longitudinal wave, longitudinal pressure wave. But also rock can be twisted against rock, and then it's a twist, a twist, a twist, or this way. And that is a tensorial wave, different dispersion relation, different speed of sound, and so on. Now, electromagnetism doesn't have longitudinal degrees of freedom, neither does gravity. So ultimately, it turns out that hij has only 2 degrees of freedom. And let's call them Vk. Let's call them Vk of lambda, with lambda running from 1 to 2, or sometimes it's called a plus and an x. We can do polarization decomposition. So the field Pij, remember the Pij is the Hij multiplied with that scale factor A, and also this 1 over square root of G and so on. So the Pij field can be written as the sum of 2 polarizations and then 2 basis matrices, 1 matrix for each polarization and for each momentum vector k. And then you have these prefactors here. And the lambda runs only from 1 to 2. So now we're left with only 2 fields. For each momentum k, we have only 2 fields, 2 degrees of freedom. So overall, we have 3 degrees of freedom, the r, and the 2 polarization degrees of freedom of the gravitational waves. The epsilon matrices obey these conditions. Here they are. These conditions are these are the conditions that we saw earlier, namely that the H field obeys this, and that, just translated into conditions for the basis matrices epsilon for the polarizations. And so what we end up with is an equation of motion for each of the 2 polarization degrees of freedom. The V field is having, so we have a 1 V field for every momentum. For every momentum we have 2 V fields. Lambda can be 1 or 2, which are the 2 polarization directions. And each of the polarization directions has, independently of the other, obeys a Klein-Gordon equation of the usual kind, where this is really exactly the Klein-Gordon equation that we've always considered. So our next goal will be to quantize the U field, which, if you remember, is the rescaled R field, so as to get rid of the friction term, and to quantize the P field, which is the rescaled H field, in order to get rid of its friction term. So we are going to quantize them and then calculate the quantum fluctuations, the size of the quantum fluctuations of the R field and the size of the quantum fluctuations of the H field by doing the quantum field theory of those 2 fields. And in order to, we will not just we will not be interested in the size of those quantum fluctuations at arbitrary times. We will be interested in the size of those quantum fluctuations after horizon crossing. Okay, because after horizon crossing, they no longer change. If you remember, the size of the quantum fluctuations freezes after horizon crossing. So we will calculate what the size of these quantum fluctuations is after horizon crossing, because that's going to be the size of the quantum fluctuations when inflation ends. That's when they will be imprinted in the CMB. And it will be slightly non-trivial because we cannot simply reduce what we did before in this course, because we did de Sitter. We'll have to do a slightly weaker version of an expansion. It's not quite exponential, it's a little sub-exponential. And what we will do is use power law inflation. So we assume that here we model spacetime as having expanded, not quite exponentially, but with a very high power. And what we expect here is that the fluctuations of R give us local spacetime expansion or shrinkage, will give us the temperature fluctuations, therefore, of the CMB that we see today, because the photons would have had to climb out of a gravitational well or come down from a gravitational hill. And then there are the fluctuations of H, the quantum fluctuations of the metric itself. We are quantizing gravity here, after all, right? At least perturbatively. And how would that show up? Well, it shows up in part in the temperature fluctuations, but it's impossible to distinguish that from the temperature fluctuations caused by the R. But there's another signature of these fluctuations in H, which is that if there were these primordial gravitational waves, they should have led to a polarization preferential climbing out of the potential wells and coming down from the potential hills, which means that the polarization of the cosmic microwave background shouldn't have been completely isotropic, but should have been modulated by this H field. And that would show up as a particular component of the polarization field in the cosmic microwave background. If you consider the cosmic microwave background, it's heat radiation from everywhere. But instead of just measuring the amplitude or the temperature, you can also measure the polarization. And there's a bit of polarization in the CMB. And you can map the polarization as a vector field in the sky. Now, as a vector field, you can decompose it into curl and gradient. It's a little non-trivial because it's not R3, it's really a surface of a sphere, but you can work with those projections. So you can decompose the polarization field in the sky into a curl and a gradient part. And there are several sources for curl parts and for gradient part. Now, luckily, there are not many sources for a curl part to the polarization. This is one. This would lead to a curl contribution, to a contribution to the curl of the polarization in the sky. And BICEP 2, exactly 2 years ago, was announcing that they've seen that. Now, what they saw was very likely just foreground, another source of polarization. But it doesn't mean that it doesn't exist, that they haven't seen it. It's just that nobody has seen it yet. And there's a huge effort trying to see that polarization, seeing curl polarization in the CMB in a way that can be distinguished from any foreground. That would be fantastic, because not only would we see gravitational waves, which we've seen with LIGO, we'd see quantized gravitational waves. Not directly, but pretty direct evidence for quantized gravitational waves. Okay, but this was all anticipating. Next time we'll actually go through the quantization. Yep?
In the whole approach you described, you have a classical background around which you have a quantum field basically operate. Ultimately, you would like to do it all quantum mechanically. Mm-hmm. How much have people been able to move through that?
Well, there are basically two ways to go about it. You can either try to cook up a theory of quantum gravity And there are several approaches for that, and you know how difficult that is. But that's what really it would take. And the other approach is to just try to go higher in perturbation theory here. And that too is being tried. But these are really very different things, and the ambitions are different. Here, if you go higher in perturbation theory, you might improve your match between theory and experiment and learn about models. But you're not going to get quantum gravity from it. And ultimately, if you cook up a theory of quantum gravity, you may have a beautiful theory, but it's generally very hard to boil it down to concrete predictions. Yeah, so there's much work to be done to bridge that gap.
The quantization that we're going to do next time,
Mm-hmm.
as quantum field theories on like the slices, like 3-dimensionally or 4-dimensionally?
Oh, we need to do it 4-dimensionally, yeah. It will be very similar to what we did previously. We will study how the expansion of an underlying space-time is affecting the size of quantum fluctuations of a field that lives on it. And this is going to be the U field and the P field, yeah.
It's like basically just like a free scalar or something, but somehow the mass is like growing or shrinking or something.
Yes, it's basically 3 free scalar fields. It's the Mukhanov variable, the scalar thing that, you know, the R field or the U field, which is rescaled. It's this one, and then the 2 polarization degrees of freedom. And they don't see each other. To the order of perturbation that we work with, they don't interact with each other. And each one of them is just living on the background of an expanding space-time, where the H field goes with the A itself, and the R field, the Mukhanov variable, goes with the Z. But basically, yeah, they're just evolving on a background space-time, and mathematically speaking, and the non-triviality of the quantum field theory comes about because the frequency of the mode oscillators is non-trivially time-dependent. And in particular, the mode oscillators at horizon crossing will go from having this kind of potential to having an inverted potential. And that is, as we discussed in great detail, that is the reason why quantum fluctuations will be amplified. And so we'll have to simply use the same machinery that we had before, except not the sitter. It's going to be a somewhat less dramatic expansion. Yep.
Remember when the bicep experiment was talking about their results? They gave some parameter in terms of some R, in terms of the tensorial part.
Mm-hmm.
So what is that R relative to H?
Okay, so basically it's how slow the slow roll is. And as we will see next time, even though the A field, even though the scalar and the tensor perturbations are calculated independently, they are calculated on the basis of the same scale factor, A of eta. And so there is a close relationship between the predictions of the one and the predictions of the other. And in particular, if the slow roll was very, very slow, then we wouldn't expect there to be much in the way of gravitational waves. So if, on the other hand, we do see gravitational waves, then this would indicate that it's not that slow a roll, and that would have implications also for the scalar part then. So there is a relationship between the two. In fact, there is a so-called consistency condition between the predictions of the scale for the scalar part and the tensorial part, and that is quite a non-trivial prediction of inflation. If we can get a handle on how big the tensor fluctuation spectrum is, and perhaps even measure it out. I mean, measure the spectrum, measuring not just that there are primordial tensor fluctuations, which would be a big deal, but also their spectrum. So how do the fluctuations amplitudes scale with the wavelength, or the angle in the sky? If we could measure that, we could plug it into that consistency condition. And if that consistency condition came out right, so if the slope of the observations of how the scalar perturbations scale and how the tensor perturbations scale, if they match that consistency condition from inflation, then I think some folks would get a Nobel Prize for inflation, because that would be very hard to explain otherwise. So it's one of the reasons why people are so keen to measure the tensor fluctuations, the curl paths. Right? Okay, see you next time.